Hello everyone, this is Yung. It's my pleasure to share about our paper, Automatic Textual Normalization for Hate Speech Detection. These days, the growing stream of social media users attracts more researchers to conduct studies on user-generated content. However, social media texts often comprise non-standard language, which can pose challenges in interpretation. Therefore, it is important to normalize social media text, making it more accessible for NLP models to solve the problems. In our research, lexical normalization is defined as the process of transforming text data into a small standard form. This procedure helps converting the informal, dynamic nature of social media content into interpretable data. While textual normalization has been studied significantly in various languages, particularly in English, the literature review on Vietnamese is limited. Most current system is designed for text-to-speech applications. However, the definition of non-standard word in text-to-speech differs from that in our study. Consequently, those methods are not directly applicable to our case. Also, several studies have focused on Twitter data, which is not a widely used social platform in Vietnam. Other studies often rely on handcrafted rules which may not cover all Vietnamese non-standard words. Recent research often employed a two-step approach involving a detection and a normalization stage. Though this method handles the problem well, its architecture is too complex and domain dependent. To the best of our knowledge, we are the first to tackle Vietnamese lexical normalization within the social media context and to propose the implementation of a single model sequence to sequence for the given task. Within the scope of our research, we aim to make three contributions. First, we created a dataset called Small Lexicon VHSD, which addresses the issue of normalizing Vietnamese social media text. Secondly, we employ sequence-to-sequence models to translate Vietnamese comments from a non-standard structure to a standard form. And finally, we did hate speech detection on both standard and non-standard data to prove the significance of textual normalization in enhancing the performance of hate speech detection. So this is how we create our dataset. We VHSD is a dataset designed for hate speech detection task. This dataset contains more than 33,000 comments. In our research, we selected the first 3,400 comments. In our annotation settings, a crew of 5 annotators participated. Each annotator labeled 1,360 comments, and 2 people labeled each comment. All annotators follow an annotation guideline to optimize the inner annotator agreement. Generally, an annotator should fix the tokens that he thinks they are non-standard, mark them with a talk sign, and show if he is certain with his answer or not. We use two measures in order to evaluate inner annotator agreement. The code has kappa coefficient E employed to determine the agreement regarding whether to normalize that specific token. Same candidates qualifies the frequency at which annotators align in their textual normalization. We define the lexical normalization task as a machine translation problem. We apply the sequence-to-sequence model and its two variants, S2 as self and S2 as multi. A non-standard comment is represented as an input sequence of T syllables X. We expect sequence-to-sequence model to generate an output sequence Y having length L with the same meaning as sequence X. The architecture of S2S model is based on the encoder-decoder framework. To better encode each token, the encoder has two LSTMs, forward and backward. which read input in the opposite directions. For each token, states of the two LSTMs are concatenated. The decoder uses source presentations from the encoder to generate the target sequence. At different steps, the decoder may need to focus on different source tokens. This is when attention comes in use. Hidden state of the encoder is used to compute attention vector. Then hidden state of the encoder is combined with attention output to get an updated representation, which is used to predict the next token in the target sequence. In model S2R self, we replace all tokens in the input string, which needs no normalization during training, with a special symbol self. In model S2R multi, we first convert tokens with a single normalized format using a predefined mapping dictionary, and then translate tokens with many adjustments leveraging the S2S model. We use two metrics to evaluate the performance of textual normalization tasks. We use F1 score to assess the appropriate labeling rate for tokens that need to be normalized. Blue score is a popular metric for machine translation tasks, so we use it to compare the results of baseline models. In this experiment, we will perform hate speech detection using both non-standard and standard comments. We obtain normalized data generated by S2F multimodal. The challenge with hate speech detection is detecting harmful content on social media. The learning model receives the comments, process them, and output the corresponding labels, including clean, offensive, and hate. We keep the settings and own training parameters matched precisely to those in the original research by Hansen Liu. We predicted labels using model text CNN and GRU and evaluated the performance using F1 micro, F1 micro, and accuracy. After annotation, the Cohen's kappa coefficient received a 0.9, and same candidates were measured at around 0.75. Both measures indicate that the normalization process is generally effective and the text have been labeled consistently and accurately. After removing all comments with a non-standard word, the dataset size drops to 2,181 comments, and the dataset was randomly divided into trend, validation, and test set with the ratio of 8:1. This table shows the total number of tokens and non-standard tokens that need to be normalized in the dataset. Statistics show that non-standard words just account for a very small percentage in our dataset. This table shows that the textual normalization results are not impressive, since all metrics are lower than 70%. The S2F multimodal has the best ability in textual normalization. The results obtained on the S2S model are close to S2F multi. However, S2S self model received the lowest results on both metrics. This is because it's the input string lacks important information when substituting self into standard tokens. Therefore, S2S self cannot take advantage of the context and misinterprets the comments. While S2S multi ensures that tokens with a unique interpretation are correctly transformed during training, increasing the sentence context reliability. Nevertheless, the traditional S2S model does not guarantee the correct translation of those tokens, so in some cases, S2S multi provides better translations. Another finding is that if the sentence is too long or too short, the model's error rate is higher. Therefore, sentence length adjustment can be an essential aspect to improve the performance of these models. So this table shows that using textual normalization improves the accuracy of hate speech detection task by 2% on F1 micro and accuracy, and about 6 to 7% on F1 macros on both text CNN and GRU models. We conclude that compared with the usual processing steps, textual normalization increased hate speech detection performance in this case. So, in short, the study we have created a dataset and models to address the issue of normalizing social media Vietnamese text. In particular, we gain a good inner annotator agreement in the annotation phase, which ensures the quality of the dataset for deepening models. Furthermore, we normalize non-standard tokens by using sequence-to-sequence models. The findings demonstrate that the machine learning models were moderately successful but challenging in normalizing text as all metrics are below 70%. However, our research shows it sufficiently boosts the hate speech detection performance. However, the dataset size is relatively small, which may cause a context limitation in lexical normalization. Manually labeling the data was laborious and time consuming. Another challenge in our study is the long training time of sequence to sequence models. So, in the future works, we aim to enlarge the dataset with a semi supervised approach to save time and effort. We also wish to broaden the scope of this study to other NLP downstream tasks besides hate speech detection, which strengthens the supporting role of lexical normalization in multiple NLP applications. Thank you.